Okay, welcome everyone to revision of chapters 1 to 3. Basically, I'm just going to be going through how I answer sort of difficult questions in chemistry, because often the questions are actually just overcomplicated, and they are done by VCA, quite common, as you can see here, where they just put all random numbers just to try and confuse you. But hopefully I can break it down. Now, just the first thing you need to keep in mind is that there are only a couple of things we need to watch out for when answering stoichiometry types of questions. These are, one and foremost, mole ratios. Now, you don't always have to know the full equation to determine mole ratios. Okay, so often we can determine a mole ratio just by seeing our starting reactant and our product, and we can determine the ratio between them. So I'll show you how to do that. The second thing is, are there any aliquots? I.e., from our beginning sample to the thing that we're performing the analytical test on, is there an aliquot? If there is, the moles will decrease to the aliquot. The concentration is the same. And the mass decreases, because remember, moles equals amount. In other words, number of atoms. It's like a number of atoms, but it is really N times Avogadro's number equals number of atoms. But see how it kind of shows us how many atoms are there. So less atoms, less mass. You've just got to keep that in mind. And 3, are there any dilutions? Because if there's a dilution from our sample to our analytical test, concentration reduces, moles is the same, and guess what? Mass is the same. So now I'm going to show you how I would tackle a sort of difficult VCAR question, which is the state scored 30% on. Okay, or actually 13 scored full marks. So first of all, we're just going to have a read of the question. It says, phosphorus is an essential ingredient in plant fertilizer. The phosphorus content in the fertilizer can be determined as a percentage by mass of P2O5. So in the end, they want you to do the percentage by mass, which would be the mass of P2O5 in the fertilizer divided by the mass of the fertilizer times 100. That's what they want you to get to. Okay? So it says that we've got the mass of fertilizer. So already we've got this bottom value here. So we have our fertilizer sample. Okay. Oh, I think I do actually have enough room on here. We have our fertilizer sample. And that weighs 3.256 grams. Okay, it is then mixed with 40 mils of water and the insoluble residue removed using vacuum filtration. You guys have done that in all gravimetric procedures because we need to get, remember why we filter? We need to get, this will be insoluble and this will be at the bottom, the filtrate will be our soluble ions that we want to precipitate, Anyway, so we get rid of all the insoluble stuff. That's not important. The important thing is we've kept all of our atoms of interest in the filtrate. 45 mils of this particular solution is added to the filtrate, followed by ammonia. A white precipitate forms. This precipitate is filtered, washed with deionized water, and we get a mass of our precipitate as 4.14 grams. So precipitate mass is 4.14 grams. That is also important, okay? The formula is known to be this, okay? So what you've got to look for is, were there any aliquots, or is all of the mass in here and the moles in here present in our precipitate? Which it is. No, they never mention an aliquot, they never mention that a portion was taken, so no aliquot. Were there any dilutions? There were a couple of when we added water and everything like that, but we're not working with concentrations, so N will be the same as in the original sample. Now the second thing is mole ratio. Now, the easiest way to do that is by looking at your elements of interest. The phosphorus content in fertilizer. That means that all of the phosphorus here must be present in our precipitate, which is here, okay? Now, we don't know the reaction between the two. It's actually very hard to produce. But we know the mole ratio because P2O5 is in our fertilizer. That reacts with something to produce MgNH4PO4.6H2O. If you wanted to write a reaction, you could do, okay, the precipitating agent is MgSO4.7H2O plus P2O5, and we also know plus NH3 produces NH4PO4. So basically you have to count. Okay, so we need two of these. We need two of these. And then we have 7H2O, which is nearly impossible to balance. But VCAR doesn't want you to balance it, as it's not in the study design. All they want you to know is that P2O5 into this ridiculously long precipitate with PO4 is a 2-to-1 ratio, or 1-to-2 ratio, because there is one P here and that's what we're looking for. So we would need two of these whole compounds to balance with a compound which has two P's. That's all you need to know to answer this question. Then we know that the molar mass of P2O5 is 142. The question tells us the molar mass of our precipitate is 245.3. And remember, grams per mole for molar mass. Now, in answering the questions, all you need to do is work out that the moles of your precipitate is mass over molar mass, which is 4.141 divided by 245.3 equals 0.0169 mole. The moles of P2O5 equals a half times the moles of the precipitate, which equals 0.0084 mole. Then the mass of the P2O5 equals moles times molar mass equals 0.0084 times 142, which is 1.199 grams. All of this mass must have come from the original because there was no aliquot. So the percentage is 1.199 divided by the mass of the fertilizer times 100, 36.81% to 4 sig figs, because even though this has 3 sig figs and this is 2 sig figs, this is 4 sig figs, well, this is actually 1 sig fig, this is 1 sig fig, we only take into account the values we use to calculate. That is the only way we count sig figs. So here, this is the only value, this and this are the only two values that we actually used that have importance of sig figs. The molar masses don't, they are assumed unlimited sig figs. Alright, so the next question. When it is heated above 100 degrees, it is completely converted into MgNH4PO4, so into another compound that obviously is anhydrogenous, while this one is a hydrated version. Okay, so when it is converted into that anhydrogenous version, according to this equation, would the calculated percentage by mass of this be higher or the same or lower as in part A? Okay, if it had been deliberately heated above 100 degrees to convert this precipitate to this precipitate. Okay, now this question might fool you because you might think the mass of our precipitate is less, okay, and that might have an effect on our perception of P2O5, meaning that we would have a lower percentage by mass. But that would only make sense if we were taking the mass of this, but we're assuming the molar mass of this. So really it should be the same because we are deliberately heating. So although the mass of precipitate will be lower, the molar mass of precipitate will also be lower. Okay, no P was lost during this process. Okay, so the important thing is we can use any precipitate that we desire when doing gravimetric analysis as long as it has a known formula. Because once we know the formula, we can use the correct molar mass. Okay. Now, the next question we're going to go through is also a fairly difficult question. So that was question 4. So just flip over, and I would suggest pausing it to try and answer the question. Okay. So now, so this question requires us to determine X. The number of water molecules in a hydrated sodium carbonate was determined by placing 14.06 grams, so of a piece of this hydrated, this should say, in a desiccator. Okay, so that's just a heater. After sufficient heating, this much remains. So this is the mass of Na2CO3 with water gone. Okay, so basically we can determine, we have the mass of Na2CO3.xH2O. The mass of this equals 14.06 grams. The mass of Na2CO3 equals 5.21 grams, and the mass of H2O equals 14.06 minus 5.21 grams equals 8.85 grams. Now, once we have the mass of this and the mass of this, this is just a mole ratio. It's going to be 1 to something. Okay, so basically we're going to be treating it like an empirical formula. because really the empirical formula is just trying to identify the mole ratio. Okay, so what we do is the moles of Na2CO3 equals mass over molar mass equals 5.21 over 106 equals 0.0492. The moles of H2O, on the other hand, is 8.85 over 18 equals 0.492 mole. Divide by the smallest. Gives us a ratio of 1 to 10. So X equals 10. So the actual compound would look like Na2CO3.10 H2O. So just always complete it like an empirical formula. Okay, next question. Here we get to I believe, back titration. Okay. So remember with back titrations, what you're actually doing is you are taking a weak base, for example. Then, in this case, I'm not sure if it's exactly a weak base. Okay. But usually back titrations, we need back titrations because they don't produce a sharp endpoint even when put with a strong acid or base. So weak base react excess with strong acid. So what we do is we have a weak base, let's say calcium carbonate, and then we add HCl excess. We then take this, which has HCl excess and the products of this reaction, but no more calcium carbonate, and we react it with a strong base. And then this is regular titration. This is just an excess reaction. Okay, in this case, this many grams of pure acid. So in the end, because we've got an X, we're definitely going to be using molar mass equals little m over n. You only use that really when you're trying to determine an unknown compound. So just keep that in mind. So that many grams is added to exactly 100 mils of sodium hydroxide. The reaction occurs according to this, so it's a 1 to 2 ratio. The sodium hydroxide is in excess. This excess sodium hydroxide requires this many mils of HCl for neutralization. Okay, so we know that it's NaOH plus HCl produces NaCl plus H2O, 1-to-1 ratio. Calculate the amount in mole of NaOH that is added to the acid initially. This is very easy. Equals CV equals 0.1 times 0.105, 0.0105 mole. Okay. The amount in mole of NaOH that reacts with the acid. This is the harder part, because we know how much is initial. We have to work out how much is in excess. Now the way we do that is by using the HCl that was required to neutralize it. So the moles of HCl that reacted equals CV equals 0.197 times 0.02521, 0.00497 mole. Then the moles of NaOH left or in excess equals the moles of HCl that required to react with it, 0.00497 mole. Whoops. So the moles of NaOH that reacted with the acid equals the moles of NaOH initially minus the moles of NaOH in excess equals 0.0105 minus 0.00497, 0.00553 mole. Then the molar mass. So the moles of H2X that reacted equals, using the mole ratio, unknown over known, a half times the moles of NaOH equals 0.00553 times 1/2 is 0.002765. Now, the molar mass of H2X equals mass over moles equals equals 150 grams per mole. Don't forget to put your units in. Okay, so another back titration, not too many left. Another back titration. This one is a typical back titration where we start off with something weak. Here we have a weak acid and a strong base that will be in excess. Okay, now plants are unable to directly use the nitrogen present in air. So basically, nitrogen is required for the reduction of proteins. Okay, thanks for that. Didn't really need to know that. Okay, we have a mass of our fertilizer. Now this mass of fert will only be used at the end when we are determining the percentage by mass, which I'm guessing, there you go, how surprising. Okay, so it was boiled with 25 mils of 1.025 m NaOH. The equation is as shown. That's nice of them. The completion was determined when a piece of universal indicator placed in it did not turn blue anymore. This is like your sack. Okay, when it was not changed to a blue color because universal indicator goes blue when there is NaOH. It was placed at the surface though because there is ammonia produced, and because this is an acid, this is a base. So when ammonia wasn't being produced anymore, it meant that all of this was gone. Whoops. So what was the percentage by mass? So basically it didn't hurt. Then we had the titrated with HCl. So what did we do? We had it in a conical flask. We had excess NaOH and we had NH4+, that was in our fertilizer. Then all of the NH4+ is gone and the excess NaOH was reacted with 0.2130 m HCl and it required a titra of 19.75 mils. The excess NaOH was, so the initial NaOH that was added was that many mils of 1.025 m concentration. Now, what was the percentage by mass? So first of all, mole of HCl required to react with excess NaOH. Oops. The moles of HCl equals CV 213 times 0.01975. The moles of NaOH in excess equals the moles of HCl required to react with it in excess equals 0.0042 mole. Happy? Now, 2 moles of NaOH initially equals CV equals 0 point, where is it? 0.025 times 1.025 equals 0.0256 mole. The moles of now number 3, the moles of NaOH react equals initial minus excess equals 0.0256 minus 0.0042 equals 0.0214 mole. Now the moles of NH4 plus in fertilizer, because there were no aliquots and there were no dilutions, meaning all of the moles here that reacted with the NaOH was in the original sample, equals the moles of NaOH, because it is a 1-to-1 ratio, which is 0.0214 mole. Now the mass of NH4 plus equals moles times molar mass, 0.0214 times 18, 0.0386 grams. The percentage equals 0.0386 divided by, is it 0.0386? Sorry. No O there. Equals that divided by 1.453 times 100, 26.5%. Because again, 3 sig figs from this value. That's the least significant. Okay, now these ones were present in Head Start and a few of you got them incorrect. So we'll just go through them. Write the formulas for the following compounds. Unfortunately, hydrogen peroxide you're just going to have to remember as H2O2. Quick revision of oxidation numbers. Hydrogen still +1, making oxygen a -1. CuCl2. Now naming it, we do copper, but because it's a transition metal, we write copper to chloride. And let's do some more oxidation numbers. If this is -1, giving us a total of 0, there are 2 Cl's with a -1, giving us a -2, so copper has to be a +2. Okay, now this one is a bit of gases. Just to keep in mind, PV equals nRT, so quick revision. N obviously has to be in moles, R is 8.31, T is in degrees Celsius, so in other words, is in Kelvin, so in other words, degrees Celsius plus 273. Volume is in liters and pressure is in kPa. So to get from atmosphere to kPa, you can get that from your data book. But 1 atmosphere is 101.3 kPa. Volume 0.017 liters. And then the temperature is 34 plus 273. So once you put that into the N equals 101.3 times 0.017 divided by 8.31 times 34 plus 273, 0.00067 mole. Then to get to mass, times it by 32 equals 0.022 grams. Okay, the next one. 4.5 grams of sodium chloride is added to 150 ml of water in a volumetric flask. Okay, then it is diluted to 80 mils. So what you could do is work out the concentration in the initial volumetric flask, then do C1V1 equals C2V2. But something easier is because it's a dilution, moles is the same. So why don't we just work with moles? So the moles of NaCl equals mass over molar mass equals 4.5 divided by 58.5 is 0.077 mole. Concentration is moles over volume is 0.077 divided by 0.8 liters is 0.096 concentration. Now this one's important. dm to the power of 3. You might get a little bit confused about what decimeter means because you haven't really seen it before, but you have to know, just in case VCAR uses it, decimeter to the power of 3 is a litre. And then if you were to work with centimeters to the power of 3, it would be 1 centimeter to the power of 3 equals 1 milliliter. Okay, so really it is 23.4 liters, and then at this and this. And I'm sure you can do it now, but I'll write out the answer anyway. Moles equals PV over RT equals 1.5 times 23.4 divided by 8.31 times 15 by 2, plus 273, 0.015 mole. Then we're doing the next one. Okay. If 3 grams of NaOH is added to 500 mils of HCl, so making sure we got our mole ratio right, will the resulting solution be acidic or basic? What will the pH be? Because we're given enough information to work out the moles of 2 reactants, this is an obvious excess limiting question where we have to work out the moles of each. Now, I would usually say pick a known, then work out your unknown, what you expect, compare it to your actual. But because it's a 1-to-1, we can just work out the moles of each and compare, and whichever one is greater will be excess. So the moles of NaOH equals mass over molar mass, 3 over 40, 0.075 mole. The moles of HCl equals CV, 0.5 times 0.1, 0.05 mole. So therefore, HCl is limiting. Okay. Now, the moles of NaOH, therefore, to answer the first question, if the acid is limiting, the following solution will be basic. Now, to find out how much NaOH is left over, we do the moles of NaOH initially minus the moles of NaOH react. Initially we have 0.075 mole, and the amount react will be equal to the amount of HCl that is there, because it's a 1-to-1 ratio and HCl is limiting. So minus 0.05 equals 0.025 mole. The concentration of NaOH equals N over V, 0.025, divided by the volume, which is 0.5 m. the concentration of OH equals the concentration of NaOH because it's 1:1. Equals 0.05 m. Now we're at 25 degrees, so we could just do POH, but I'm going to do this one. Kw equals concentration of H3O plus times the concentration of OH negative is 10 to the negative 14. So the concentration of H3O plus or H plus, same thing, equals 10 to the negative 14 divided by 0.05 equals 2 times 10 to the power of negative 13. So pH equals negative log concentration of H plus equals negative log 2 times 10 to the negative 13, so it's negative log 10. Equals 12.7. So even after the reaction, because NaOH is in excess, the pH will be 12.7. Second last question. What volume of HCl is needed to neutralize 2 grams of calcium hydroxide? Now, this is not an excess limiting. They're actually getting you to work out how much is required for stoichiometric ratios. So importantly, we need to write a reaction. CaCl2, this is the aqueous. Calcium hydroxide is slightly soluble. I believe it is slightly soluble. Give me a tick. Okay, now, is it slightly soluble? Yes, okay, so, yeah, so we can just do aqueous for that. Now, the moles, we have to start off with the moles of our unknown, which is, the moles of our known, which is calcium hydroxide. Mass over molar mass equals 2 over 40.1 plus 16 by 2 plus 2, 0.02699 mole. The moles of HCl equals 2 times the moles of calcium hydroxide equals 2 times 0.02699, 0.05398 mole. The mass, the volume of HCl equals N over V, N over C, 0.05398 divided by 0.125 equals 435 milliliters. So 0.435 liters. Finally, this question was done horribly by the state, so I thought I'd go through it. It is a limiting excess. So, just wanted to know what it's called, bornite. When 1 mole of bornite and 1 mole of oxygen react, they react according to the equation. Okay, no reagent is in excess. So, then to make things easier, we pick a known. Let's just go, this is our known. Okay, so let's just say our known is O2. That means our unknown in other words, we want to find out how much we'll react with it, or how much we expect of Cu3FeS3 equals unknown over known, which is 2/7 times 1. Okay, now that already tells me that we expect 2/7 mole, which is less than 1. But we actually have 7/7 mole, don't we? So because we expect less than what we have, this has to be in excess. In excess. How much is it in excess? Well, how much will be left over? Like we always do it. The moles initially minus the moles react equals the moles initially is 7/7 minus the moles react, which is 2/7, equals 5/7 mole. In other words, C. Okay, I hope you enjoyed that.